Hello everyone, my name is Anirban Sengupta. I will be talking today about our group's research which got published in Journal of Magnetic Resonance Imaging recently. The title of our article is Glioma Grading Using a Machine Learning Framework based on optimized features obtained from T1 perfusion MRI and volume of tumor components. I will briefly present the research work. For detailed information, please refer to the published article. Gliomas are the most prevalent primary brain tumors in humans. Gliomas are classified into low grade, which consist of grade 1 and 2, and high grade, which consist of grade 3 and 4, as decided by rules set out by World Health Organization. Prognosis and treatment planning of gliomas depend on their grade. There has been a number of research studies in recent past to predict the glioma grade using different MRI techniques. T1 perfusion MRI is one such MRI technique which provides a number of parameters which are quantitative in nature. These parameters constitute hemodynamic parameters such as CBV and CBF, tracer kinetic parameters, and piecewise linear model parameters. There are some challenges in glioma grading. The currently used way of ROI selection based on hotspot method is prone to error due to subjectivity among radiologists. It is difficult to differentiate between intermediate groups such as grade 3 versus 4 and 2 versus 3 because of overlapping characteristics between grades. It has also been reported that glioma grading can get affected due to the inclusion of prominent vessels within the ROI. Finally, machine learning algorithms such as support vector machine or SVM have recently been shown to be useful for classifying gliomas into different grades. One important aspect of classification task having multiple features is to obtain the optimal feature set that provides the best classification results. Some machine learning algorithms like random forest or RF perform feature selection as part of their overall operation. The purpose of this study is to devise a method for differentiation between intermediate glioma grades as well as multiple glioma grades using T1 perfusion MRI parameters as well as conventional MRI features. The hypothesis behind this study is that if T1 perfusion parameters are combined with tumor volume parameters, it can improve glioma grading by providing complementary information. 53 glioma patients were recruited for the study, of which 26 were grade 4, 12 were grade 3, and 15 were grade 2. An additional data of 13 glioma patients were acquired for held-out validation in this study. MRI protocol for this study included the acquisition of conventional MRI images, data for T1 map, and data for T1 perfusion MRI. The first step was to compute the T1 perfusion parameter maps and use them to segment the glioma tumor region into its different subparts according to a previously published method by Sengupta et al. This figure shows the entire glioma tumor as delineated by the hyperintense region on FLAIR images being segmented into different subparts. Different colors refer to different tumor subparts. To generalize the process of ROI selection from both enhancing and non-enhancing glioma, enhancing and non-enhancing component was combined to constitute the ROI, which was used for glioma grading in this study. Next, we needed to remove vessels from the ROI as mentioned before. This figure shows the removal of prominent vessel from the total tumor region using CBV corrected normalized white matter map. The vessel here is segmented out from the selected ROI based on its hyperintensity on CBV corrected normalized white matter map. This figure shows the process behind formation of the feature vector which is used for classification purpose in this study. Hemodynamic parameters such as CBF, CBV, tracer kinetic parameters such as lambda trans, K trans, VE, VP, and piecewise linear model parameters such as slope 1, slope 2, BAT, and beta are obtained from each voxel of the 3D ROI volume of each patient. The feature matrix of each patient contains a particular statistic of all the T1 perfusion parameters, which can be either the mean, median, etc., as calculated from the 3D ROI. The feature matrix also consists of volume percentage of different tumor components, which are enhancing tumor percentage, edema percentage, and necrotic percentage. This figure shows a box plot representation of 8 representative features for grade 2, 3, and 4. The box plot results show that there is no clear-cut threshold based on a single feature, and there is some amount of overlap between all the grades. 7 different statistics of T1 perfusion parameters were used for optimization, which were mean, median, mean of the values above the 95th, 90th, 85th, 80th, and 75th percentile value. The statistic, which had maximum AUC averaged over both the binary classification, was finally chosen for final glioma grading. Here it was found to be the mean 90 statistic, as shown in the table of this slide. A SVM classifier was used in this study. Both linear and RBF kernel was used to optimize the classifier. The classifier was also optimized based on its hyperparameters such as C and gamma. We used 12-fold cross-validation technique in this study for obtaining the classification accuracy. Also, for the multiclass classification, a 1 versus rest approach was followed. Next, feature selection was performed. At first, all the features were combined to obtain the 12-fold cross-validated classification accuracy. Next, we used sequential backward selection or SPS method. Finally, we used random forest classifier to perform feature selection. For grade 2 versus 3 classification, it was found that SBS obtained optimal feature set reduced the error from 11.1% to 7.41% compared to using a combination of all features. Error was further reduced to 3.7% when RF chosen feature set was used. The sensitivity and specificity also improved correspondingly. The optimal features provided by the RF classifier consisted of some of the T1 perfusion parameters and all the tumor volume component features. Similar results were obtained for grade 3 versus 4. It was found that the minimum error of 5.26% was obtained by RF chosen feature set. Multiclass grading results show that taking optimal feature set obtained from RF classifier provided minimum error following the same trend as before. The optimal feature set included all hemodynamic and tumor volume features, some features from PL model, and tracer kinetic model. In conclusion, the present study shows that it is feasible to obtain low classification error using the proposed methodology. The developed classifier for grade 2 versus 3 versus 4 differentiation correctly predicted 11 of the 13 glioma patients in the additional held out validation set. This further validated the robustness of the developed classifier. Volume of different tumor components are useful in the grading of glioma when used in conjunction with T1 perfusion parameters. The mean 90 statistic provided maximum AUC in ROC analysis and can be used as equivalent of hotspot area. Finally, applying feature selection helps in improving classification accuracy by removing redundant features. Thank you.